Hmm? I was in France and Germany, and then I'll be going back to Spain. So, but it's all the same time zone. So, yeah, Frankfurt was pretty warm, 27. Yeah. Yeah, not really. It was sort of end of summer, but it was a kind of late autumn. I mean, end of summer thing. Spain will be warm, just because it's a much more southern city. Now, apparently the lectures here start on the dot, on 9, right, and finish 10 minutes early. That's the plan. So you're also getting the privilege of my very first lecture at Monash. After 28 years lecturing at Melbourne University, where they start 5 minutes past the hour and finish 5 minutes before the hour, I'm now here. But there's a huge turnout. I guess now everyone is watching online. Who could get in at 9 o'clock in the morning, right? Oh, today's a good day. Oh, that's good. Well, I need you here. I need you here to actually ask me some questions. Otherwise, as I said, it'll just go faster and faster and faster until basically you won't be able to understand a word I'm saying. I can assure you, after you've just come back from Europe, getting up in the morning is also exciting. My body certainly did not want to get up. So I should have caffeinated myself more, I suspect. I wonder how this automatic recording goes. Presumably it just starts exactly at 9. All right, so there it is, 9 on the dot. So welcome to Research Methods, FIT5125, or many other numbers it goes under. So I'm going to be lecturing for the next 2 lectures, and we're going to talk about research methods, but here I'm more on the harder side, on algorithms, and how to evaluate algorithms. Okay. So we'll begin with what are algorithms. Now I hope as computer science students you already know what an algorithm is, but we'll go through it anyway, and then we'll talk about how you evaluate them, right? Because algorithms can be evaluated in lots and lots of different ways. We'll talk about some repository of resources that you can think about, particularly for this data science kind of things. And we'll look at a few case studies at evaluating algorithms. We'll evaluate a regression algorithm, and we'll evaluate, or we'll look at comparative algorithms for solving a search problem, in our case, a travelling salesman problem, which is a very, very well-studied problem. Okay, so what are we trying to do about this in this subject? Well, you need to be able to tell me what an algorithm is. Once we're finished, you need to understand why we test and evaluate algorithms. What's the purpose of that? And you need to be able to explain methods for testing algorithms, right? And then, because we'll look at different approaches to hard search problems, okay? You need to understand what those different methods are, the kind of core of them, and why we have different methods. And you should be able to perform a simple algorithm evaluation. Okay, so that's what we're trying to get to today. So as I said, please interrupt me at any time. A much more interesting lecture if I get interrupted. Okay. So, interrupted. Ask questions. It's not interrupted as a negative thing. It's, I'll be much more, if we have an interactive lecture, it'll be much more exciting for everyone, even those of you at home. Okay, so the first one we're looking at is algorithms and their evaluation, right? So, okay, so the name algorithm comes from this Arabic mathematician, Muhammad Ibn Musa al-Khwarizmi. And so you can see it came from this thing. And basically, it's a step-by-step way of achieving a goal. And the easiest way to think about that is, I think recipes is the best example, right? Because a recipe is exactly that, right? It's a simple algorithm because it's just a stream of instructions. Do this, then do this, then do that, then do that. And even some recipes, advanced recipes, have parallel instructions, right? So you might be putting something in the oven while you're preparing something else, right? So we actually have parallel algorithms where multiple things are going on at once. Okay, but what recipes don't have is loops, right? They don't have the idea where we go back and do something again, right? Or maybe sometimes they do, okay? If you're making croissants, is that a question?
That guy is Persian, he's not Arabic.
Ah, sorry. Okay, I stand corrected. It's good to see we have some, I always thought he was Arabic, that's interesting. Okay, so Persians. So a slight on all Persians feel I've misnamed, because algorithm, it's a great word, right? It's a great thing to be named after. It's a great scientist, in some sense, to get that name after you, because they're everywhere. So as I was saying, some recipes do have loops, I guess, but very limited. Like in you're doing croissants, maybe, you have to do one layer, whatever, flatten it, butter it, and then do that 4 times, right? So a simple loop. So recipes are a really good example of algorithms, but they're the very simplest kind of algorithm. And actually, they often don't have this kind of thing, like in this instruction, where you have choices. So in recipes, you're typically going to do this, do that, do that. But they will have things a bit like that. If you think about a recipe, you'll say, okay, then put it in the oven until it is brown, right? So if you think about that, that's actually something where we're repeatedly polling the state of something. So if you're building a computer program to do that, right, you'd have a vision system looking at what's in the oven, repeatedly going around the loop, looking at the image, making an evaluation, is it brown, and coming back. Right? So even recipes, if you go into them a bit more detailed, so particularly if you want to build an AI to follow recipes, then you'll have to understand them much more algorithmically than we typically do. Right? And actually a lot of the difficulty of recipes is understanding a lot of the terms. Right? So sometimes they'll say, cream the butter. So what does that actually mean? Okay, so unless you've sat next to a chef creaming butter and found out how to do that, then you don't know. All right, but as I said, they typically don't have these kind of things where we look and we make a decision and then choose an alternate path. Right? Recipes are meant to be sort of one single path approaches, but algorithms are not like that. Algorithms, we're typically making decisions and doing different things with respect to different data, for example. And computer programs implement algorithms, right? And in fact, algorithms now make the world go round, right? If you think about it, there's nothing really important going on in the world where there isn't an algorithm behind it. And some of those algorithms are very complicated, and some of them are very obscure, in fact, if you think about modern AI techniques. Right? So the actual algorithm that's running will be some deep neural net, which has already been trained. So that's actually a very simple algorithm to run, but to build that neural net might be very difficult. Okay. So let's talk about the kinds of problems we solve with algorithms. So in fact, I would claim that basically every problem in the modern world is nowadays tackled by algorithms in some way or other, right? Well, there'll be part of it algorithm. Even, it's not, you get to law contract negotiations now. We increasingly have bots that try to take law contracts and write them into some logical formalism so they can reason about them, for example, right? So even things where we think that it's not a role, there's no role for IT, increasingly there is. So medical diagnosis is another example, right? So, but let's think about just computational problems from a computer science perspective to begin with. So what are some examples of these kind of problems? So path planning, right? Finding a route through a maze, or more realistically, finding how to drive from here to somewhere else, right? It's a very common thing, and you're all probably using it on your phone all the time. Okay. So path planning algorithms, there's still lots of work, interestingly, on path planning algorithms because it's such an important question, right? How do I get from here to here via public transport, right, or walking, right? Find the different ways. Public transport has to take into account schedules and all kinds of stuff. So this is actually a very important problem, and still we're working out new ways of doing that, right? Even though this is well studied, at least in its fundamental computer science version. Sorting, okay? You must have all learnt sorting algorithms in your basic computer science. Just trying to understand the background of it. You've all done some level of computer science degree beforehand, right? Yep, okay. So travelling salesman, we'll go on to, we'll look at in more detail later, and this is a very well-studied problem, which is how do I build the shortest tour that visits a number of cities, right? So it comes from the idea of a travelling salesman who's going around have to visit all these different cities to sell their wares, but actually it's critical nowadays, it's the basis of vehicle routing algorithms, right, which happen every day. We have trucks that deliver bread to hundreds of places around Australia, thousands of places around Australia actually, and so Goodman Felder, who are the people who bake the bread, the tip top and all the common bread, they have to work out how their trucks are going to deliver every day. And there's lots and lots of, so it's not just the shortest path, which of course is about saving fuel, but there's also lots of other constraints involved in a vehicle routing problem. But TSP is the core of that. Machine translation, right, which we've got to a level where this is pretty good, right? You can use Google Translate and you get something. Okay, it's not ideal, but it's something, right? How do you translate text from one natural language to another? And it's interesting that after years and years of working on this from a very structural point of view, right, where we said, okay, we're going to work out the grammar of the text and we're going to work out what it actually means, and then we're going to take that meaning and translate it back into words in another language. It's not really how natural language translation works, right? It's much more learning big chunks and putting it all together. So it turns out that the power of data is very powerful, I guess. And graph calling. There's another very classic computer science kind of view of the world, right? And you might think, well, what's graph calling? So this is where I've got a graph and I want to make sure that no two nodes which are connected have the same colour. And you're going, is that useful? Actually, that sits inside all compilers, right? So one thing that a compiler has to do is to say, oh, I've got all these registers, all these variables that I need to store somewhere. I've only got a certain number of registers, right? So each register is a colour, and I try to make sure that variables that don't interact can have the same colour, because they can be kept in the same register. So every time you run a compiler, graph colouring algorithms are going on, right? So it may seem like a very obscure problem, but actually it's a very realistic one, and appears in all kinds of other important cases. Okay, so, and the key thing that we're going to be talking about today is that for all of these algorithms, there's lots of different ways to approach it, right? And sometimes we'll get a very dominant approach, right? In the end, after lots of study, the computer scientists will come up with the best way of doing it, right? Particularly if we have a very clearly mathematically defined problem, that'll be the case, but usually that's not the case, right? Usually there's lots of ways, and they'll have different strengths and weaknesses, and that's what we're going to be talking about today, is how do we evaluate, because we look at an algorithm and evaluate how good it is on the class of problems it's meant to be solving. So if we think about path planning problems, right, which we can use for lots and lots of different kind of problems, there's kind of some basic ways we can do search, right? So if we're looking for a path, we can do a depth-first search, which sort of says, I start at the start, and then I make a step towards where I want to go, make another step, make another step, make another step, keep on going, and did I reach there? No. Okay, then I'll go back one, and then I'll see if I go a different way, could I reach there? And then if I go back two, if I take different steps, can I reach there, right? So depth-first search means I'm going down as far as I can, and then searching at the bottom, right, and then eventually coming up a big tree of possibilities to search, and I'm going as far down as I can, right? Yep. So chess machines work so the chess kind of searches work in a depth-first way, or they tend to be more a breadth-first search, right? We'll get to that in a bit more, because, well, actually they're pretty much depth-first, but what they'll try to do is every time they come to a decision point, okay, which move do I make now, right? They're going to try to evaluate quickly which is the best one to try first, right? Because you can't, if you think about a chess search problem, right, there are so many chessboards in the universe, there's only a finite number, but there's a lot of them, right, that you can't search them all. So the whole point is to be looking at search plays, right, which gets you into good parts. And so a core thing of say, in chess is that at some point you just stop searching, right? Because you can't run to the end of the game, because ideally that's what you want to do. Like in tic-tac-toe, what you do is you just search and see, did I win? Did I win? And basically you try to find a game where if I make this move, I always win, or I never lose, right? And you can, right? And those kinds of games are called closed games. But for bigger games like chess or Go, what you do is at some point you stop and say, let's just evaluate the board and see how good it looks for the future, right? And then I'll use that to walk back and say, okay, this move tends to get me to boards which look good, right? But it is a kind of depth first search, isn't it? You have to go depth, right? You can't go breadth. You can't try every possible move at every possible level. So breadth first search says, okay, let's try all one-step paths. Okay, did I get to where I want to go? No. Okay, now let's try all two-step paths. Did any of those reach me where I want to go? Right, now I do all three-step paths. Now you can see in a game like chess, where I don't know where the branching factor is, something like 40 or something, right? Then you've got 40 here, 1600 there, right? You just can't go very deep that way. And you don't learn very much, right, by going very shallow in a game like chess. You need to go deep to find out where you go, or even better in Go, right, where you've got, okay, you've only got 19 by 19 moves at every level, yeah? So you don't learn very much without trying to go a long way. So that's breadth first search. But that can be very good. We use breadth first search for a lot of things, right? Particularly, let's say, if we have no idea what I'm trying to do, but I expect a plan to be short, then actually I'm better off trying all plans of length 1, all plans of length 2, and all plans of length 3, instead of trying, okay, let's try a plan and it might try, let's say, could be 1,000 steps. Then I'm never going to find all plans of length 1,000. And maybe I only need 3 steps to get where I want to go. If I look at all steps, all plans of length 3, then I'll get there quickly. If I try to look at some of length 1,000 and then backtrack up, I may never find the one at length 3. Right, so breadth first search is also an important part of how we tackle these kind of problems. And then a very general class, and you may have heard of these things like algorithms like A-star algorithms. Anyone heard of A-star? Yeah. And the A-star algorithm is the idea of whenever we make a choice, we're going to basically evaluate a heuristic saying how close are we to our goal, and then we're basically going to make the choice which, if we take the distance we take to get to that choice plus the distance we think, the further distance to get to the goal, that looks the best. Right, so always make the best first choice. So we'll try to go best, and actually in best first search you sort of expand the tree. We might go down a bit here, and then we go, oh no, this is not looking as good as it used to. Now let's go over here in the tree and expand a bit, right? And you do little expansions. And so if you think about it, Dijkstra is an example of that. Well, no, Dijkstra is not. Dijkstra is a kind of breadth first search, but A-star algorithms are best first search algorithms. Okay. One of the key things we do in computer science, one of the things that excites me about it, is that we devise new algorithms, right? So what we're trying to do is we're building a new algorithm which is meant to be better in some way, right? So most of the problems have been tackled before. Sometimes we just build the first algorithm to tackle a problem, right? Mainly, not that most problems have been tackled before, but sometimes we take a problem which has always been split into 2 and tackle it for the first time as one problem, right? And so when we do that, we have to do a few things. We have to demonstrate that it actually does what it says it does, right? And we have to probably test its performance. Because there's probably alternate ways of doing it, right? We need to show, when we build a new algorithm, that it's better, right? And so this is a strong part of computer science. Right? So we will devise a new algorithm or a new way of tackling something. Then we'll publish this description of the algorithm and some test results showing that it's a valuable new algorithm. Right? It's better in some groups in some way. And we can then make it available in a software repository or for commercial development, or we can spin out a company. Right? If you think about it, Google really... The start of Google came from just one algorithm or one way of ranking search pages, right? So then they said, well, that's so much better than what the other options were at that time that we can build a company just based on we have a better way of ranking search pages so we get more useful results. And there we go. Years later, billions of dollar company. So that's the best sales pitch you can give, I think, to high school students when you're saying, what subject do you want to do? Do you want to do, something which is going to be replaced by computers soon enough, like medicine? Or you don't want to do computer science where, you can be a billionaire. Although not many of us will become billionaires, tragically. There's two good ways to become a billionaire. The best way is to have parents who are billionaires. That's easily the best way. And the other way is to do computer science and be very lucky. Okay. So, when we build an algorithm, we need to demonstrate it works as intended. So how do we do that? So I feel like I'm talking too much. For those who've arrived late, ask me questions, interrupt me. As I said, it'll make for a much better lecture if you interrupt me. Otherwise, I'll just go on and I'll get faster and faster, as I said, as I warned. Okay, so the first thing we might do for an algorithm is we might actually mathematically prove that it does what we say it does, right? So we should prove, particularly if it's meant to find the best answer, right, to a problem, then we should actually have a proof that it does find the best answer, right? Now, many times we won't, right? We might be able to prove that given infinite runtime, it might find the best answer, but a lot of the problems that are out there are harder than we would expect to always be able to find the best answer in a reasonable amount of time, right? So if you've heard of classes like NP-hard problems, right, these are very important class of problems. Basically, most of the problems, interesting problems we look at are NP-hard, and we know that unless P equals NP, which is a very technical computer science thing, then we expect them to take exponential time in the worst case, which means you're not going to get very far. And we'll show some examples of what exponential time looks like. And there's worse. There's algorithms which are even harder than that, piece-based complete algorithms, which take even more time than that in the worst case. But first of all, we can build a proof that our algorithm actually works. And often that's a core part of what's going on, right? So we should also know, right, when does our algorithm not work? So this is when we're writing our algorithm description, we should be saying, okay, these are the conditions under which we assume it runs, right? Or the opposite way is to say, if this condition does not hold, our algorithm does not work, right? Because often what we'll be doing, remember, every problem has been tackled, at least usually, some way before, right? Or there's some generic methods we could apply. So we can be, one of our reasons for having a contribution, we can say, in this special case of the problem, we have an algorithm which is better than the general version of the algorithm, right? So, for example, if we're doing shortest path algorithms and the distances are always non-negative, right, then we can use Dijkstra, right? But if the distances involve negative things, then we have to use other kinds of shortest path algorithms because Dijkstra won't necessarily work correctly. Okay? So we should identify the limits and the conditions under which our algorithm works. Right, so you can think of it two ways. You can say, under these conditions it works, or you can say, if these conditions are broken, it doesn't work. And you can show examples why it doesn't work. And that's important. We can test key properties of our algorithm, right? So we can look at, what is it best at, or why does it work in this particular case, or what part of the data is important for this algorithm. And then we would often compare, right? Since we're probably not writing the first algorithm to solve this problem, we should compare with existing algorithms, ideally on existing data that people have already used, right? And using other people's software, or often we'll actually have to implement this existing algorithm again because it won't be available, right? And then we'll have to try to do a fair comparison, right? Where we take our implementation of someone else's algorithm and compare it with our new algorithm. And then we've got to be careful that we put as much care into implementing this person's algorithm, right, that already exists as ours. Otherwise, you can often get very misleading results, right? Because You spent ages and ages making sure your algorithm was fast, but you didn't do the same for the other one. Right? That's why often when you're doing comparison, you want to actually do the comparison versus with the other person's software. Right? And increasingly, because there's a lot more push now in computer science for repeatable results, right? In general, in science in general, we want to have repeatable results. We know that a lot of things, that's what science is meant to be, right? But because we get so specialized, it's often very hard to be repeatable. And so there's more and more push in the computer science world to say, okay, if you're building some new algorithm which works, then you have to make it available. Right? It has to be available so that other people can run it and test it, and they can see that they get the same results as you. Right? And there's also the whole kind of free software foundation view of that actually algorithms shouldn't be patented, and all of this should be available, and that allows us to build world knowledge and all take advantage of what everyone does. So comparison is a really key part of algorithms. And then not only just comparison, like, are we better, but then we want to say, in what way? Right? How do we compare algorithms? So we might compare them on speed. That's often something, like how fast can we do something? That's very clear. But then it's on, okay, what size of problem do we do well? Maybe our algorithm is very, very good for small problems, but not good for big problems. Or maybe the other way around, right? And often, because when we're only giving an approximate answer, or the best answer we can, then we might want to compare on accuracy, right? How good are we, if we're talking about an algorithm, let's say, which is a machine learning algorithm, how accurate are we at predicting what the future will be, for example? And finally, experiments. So ideally, we want to test our algorithm on real cases, right? That's the ultimate test. Why we're trying to develop an algorithm is to solve real problems. But we also do it on artificial cases because then we can control the cases and we can look at this variance. Like, how does our algorithm vary as this kind of parameter changes or as this kind of parameter changes, right? Typically, for real-world data, we don't have that thing available, right? So with artificial data, we get the way of sort of seeing how your algorithm interacts with various things. Okay. So, what are important properties of algorithms? So the number one important property is correctness. Yep. So it should actually answer the question correctly. Now, we have to be careful because that correctness we can change with respect to what we think. So if I think about a machine learning algorithm, okay, if I build some simple regressor, then it answers the question, right? It says, okay, you give me some test set and I'll tell you, the price of that stock. And the price will be wrong. Always, basically, unless we're extremely lucky. So is this working, right? Well, it does produce an output, right? But is it better than, let's say, a random number, right? So I need to judge, right? So sometimes what is the right output can be a bit not obvious. So if it's a more simple question like, if I give you a travelling salesman problem, and I say, find me the shortest path to connect these things together. There is actually exactly one answer, right? There is exactly one shortest path way of connecting all those cities together. Does our algorithm find it? Well, if it's a big problem, maybe not. But then it's like, okay, find me the best path that you can that joins these cities together. And then we can talk about, okay, how far off the optimal are you, right? So often, because problems are hard, right, sometimes there's a best answer. Okay, when I say sort these trillion numbers, there's one way of doing it, and we don't expect them to not be sorted at the end, right? The algorithm's correct if they come out sorted, right? It's a well understood problem, and we expect it to work however big the input. But sometimes correctness is a matter of degree, right? So if I have a travelling salesman, correctness means really just, it gives me an actual tour. An actual tour. It doesn't give me something which isn't even a tour of all the cities. It doesn't skip some cities or things like that, right? It actually does answer the question. And then there's a judgment of how well it did, how well it answered the question by how short the tour is. All right, scalability. can we handle large inputs, right? So, nowadays we have a large amount of data, right? And some of our problems can be very, very large. So if you think about this Goodman-Felder problem, where they have literally 1,000 customers that get delivered bread every day, or I think it's between 1,000 and 2,000, right? And we've got to route trucks to do this, right? So it turns out that a lot of these problems can be separated because some of their customers are in Brisbane and some of them are in, Sydney and some of them are in Melbourne, but then some of them are in country Victoria, right? So it's not so obvious how we make these problems altogether separable. So can we handle large inputs, right? Sometimes we don't need larger inputs, right? If I'm thinking about doing a school timetable, then let's say there's only going to be 50 classes in the entire school, right? 50 total different classes, not 50 different times in classes, but 50 classes of students. And we have to find something for them to do at, let's say, 40 time periods during the week, right? And really, if we can handle that problem, we can timetable the school. Actually, by the way, that's not a very easy problem to solve. Right? School timetabling is typically solved very badly and mainly by hand. So scalability is true for some kinds of problems. Yep. Question? So most schools still do it by hand, or they will typically have some kind of computer support. And the weird thing with school timetabling is, at some time or other, they bought some software to help them do school timetabling, and that changed the way they did school timetabling. So they basically have adapted their timetable to the software, right? But actually, most of the software, and the same for the university timetabling, by the way, the university timetabling should be done completely automatically by high-powered software. It's not, right? Because it's too complicated, and the software is really bad. Okay, so it's a very big search problem, and the software does it very badly. I'll tell you why school timetabling is worse. Okay, in university timetabling, we can give you 2 lectures at once, right? It happens, right? Bad luck. We just do it. In school timetabling, you can't tell the grade 3, okay, you're going to be here and here at the same time, right? And more than that, you can't tell the grade 3 that you have a period where nothing's happening. No, there's always something happening, right? So actually, school timetabling is much, much tighter. All the students have to be busy at all the times, right? And we've still got all the problems of we've got to have rooms for everyone, we've got to have teachers for everyone, right? So they typically make it simpler, right? Of course, at the very lowest levels, you just have one grade teacher has them all the time, so the timetable is much easier, right? One class, one grade, okay, very simple problem. But once you get to high school timetabling, right, it's very, very complicated because people are doing different subjects and they're doing it in different places and everyone has to be busy at all times. So it makes it actually quite a tricky problem. And the reason it's not really tackled is there's not much money in it because every school does it differently. Okay. Limitations, as I said. We need to know under what assumptions your algorithm works, right? When does it fail? What is the cases where it's allowed, is it meant to work? And can it fail, right? So there are definitely algorithms out there which just say no in the end. Sometimes not, I mean, there's algorithms that fall over for bugs, right? That's a different thing. But there are algorithms that in the end just looking for a solution and never find one in an acceptable amount of time, right? Which is essentially what happens if you take the university timetabling problem and you just hand it to the software, right? It'll produce very, very, very bad timetables, and then what actually has to happen is humans go in and fix most of the major decisions, right? Typically in a university, the hard part is there's not enough big lecture theatres, right? So they're very tightly controlled. So humans will make some core decisions about how we do the very big classes, and then we'll try to, then the software will fit all the rest of the people around that. Okay, and of course, performance, right? In computer science, we're often interested in how fast is it? How fast is this algorithm, right? Because data is big, we need to get things done faster, right? Even though computers are so way faster than they ever were. In fact, a lot of the software we produce is full of bloat because we have so much computing power we don't care. But actually there's always problems, like I said, that like the travelling salesman or these kind of things, where it's actually really, really hard to solve, right? And so we need to make the code very, very fast. How reliable is it? Right? Does it always give us an answer? Ideally, we want a software which always guarantees to give us an answer in a reasonable amount of time, even if it's not a very good answer, but it is a correct answer, right? But that might not be possible. And then we will compare it against standard benchmarks, right? So we can compare our algorithm versus someone else's algorithm, right? So that's what we're doing when we're characterizing algorithms. Okay, so proving correctness, right? So if we're tackling a well understood and mathematically precisely defined problem, then we can prove that it gives us the right result, right? So for example, we can prove by induction that merge sort actually ends up giving us a sorted result, right? And you can see the induction in merge sort is very straightforward because it comes with the algorithm, right? So merge sort says we split the input into two, and then we sort each of those, and then we merge the two together, right? So the inductive proof is to say, okay, when we split them into two, eventually we get down to one item. The one item is always sorted, right? So all we have to do to prove merge sort is correct is say, if we give it two sorted lists and merge them, the result is sorted, right? Once we've proved that, then we've proved the entire thing is correct, because you can argue by induction that there's a base case where we get down to one, and so a list of length one is always sorted, right? And then we know that every time we join two things together with our merge, they're sorted, so that means by the end, the total thing is sorted, right? So you can see there, the structure of the proof exactly aligns with the structure of the algorithm, yeah? And you can do similar things for proving, for example, quicksort, right? Similarly, right? We're going to partition, then we're going to say, okay, once we've partitioned into two parts, if we sort this part and we sort that part, then we join them together, then the whole thing must be sorted because the partition said these are all smaller than all of those. Yeah, so that's the proof. Okay, as I said, sometimes we do the opposite, right? This is part of understanding the limitations of our algorithm. So when is our algorithm not going to solve the problem or give us not the right answer, right? So typically this is more like answers, examples, right? Show why this particular clustering algorithm will get stuck at a local minimum, right? And a lot of the algorithms we use aren't going to give us back the optimal answer, right? I'll talk a bit that more later in this lecture about local and complete approaches to solving problems. So complete approaches at least attempt to find the best possible answer, but local approaches typically will just find an answer. Okay, so computational complexity is one way we talk about understanding algorithms, right? So how does it scale? And the typical way we think about this is the worst case behavior, right? So this is big O notation. Is everyone familiar with big O notation? 1, 2, I got a nod. Hands up if you're not familiar with big O notation. See, I can get whatever answer I like, right? So, hands up who is familiar with big O notation. Okay, finally I get some response, but not everyone even. Okay, I hope that you've done enough computer science that you're aware of big O notation, right? But we know that certain, right, the worst case behavior for certain kind of problems, some problems which are really well studied, we actually know exactly how complex the worst case behavior is, right? So we know to sort n objects is order n log n, worst case. And in fact, order n log n, best case. Right? There is no, for a general class of problems, general class of n objects, there's no way of sorting in less than sort of n log n steps. Yeah? Of course, when we look at things like quicksort, right, its average case or its best case is order n log n, but its actually worst case is order n squared. Right? Because we get bad partitioning values and be unlucky. It's very hard to get that if you do the random pivot selection. Very hard to get to that worst case, but it is possible. All right, if we find the distance between any two of n points, right, find the largest distance. Well, you can sort of think about that. We've got n points. We basically have to look at all the pairs of distances. So it's order n squared. Yep.
Actually, I have 看资料或这个P and NT 包括 P NT 哈 NT complete.
Yep. Okay, I'll go into that. Just let me, I'll finish this and then I'll talk about P and NP. Yeah, okay. Because that's a very interesting class of complexity, and in fact it's sort of at the core of computer science, and if you prove P equals NP, which not many people believe, then you'll get a Turing Award, and if you prove P is not equal to NP, then you'll still get a Turing Award. So it's a very important question. So just I like to put this up because we think of inverting a matrix as n cubed, right? That's the standard algorithm you'll learn to invert a matrix is n cubed. But that is not, there are better ways of doing it, right? So currently there's a way which is n to the 2.373, right? That's less than n cubed, right? And sort of every year that number gets slightly smaller, right? So 5 years ago, I think it was like n to the 2.375. Yeah? So you think that inverting a matrix, a very, very fundamental algorithm, right? We must understand by now, we've been doing this for years, we must understand how complex that is. We don't know yet. All right? So people are still looking at this. Interestingly, by the way, none of these approaches you would ever use. Okay? So this is the game about asymptotic complexity. Asymptotic complexity is an interesting way of comparing things, and it really makes sense when I talk about quicksort and I talk about n log n versus n squared, right? That really makes it, it's good to understand the difference in asymptotic complexity, but often asymptotic complexity is meaningless, right? Because if we look at our timetabling example, we're only going to timetable for classes up to size, let's say 80 classes in 80 different time periods. We're not going to timetable 100,000 classes for 100,000 time periods, right? So the asymptotic complexity, right, which just doesn't worry about the constant factors, is basically wrong, right? So none of these algorithms here, well, I might be wrong. There might be some big examples of people wanting to invert matrices where they're starting to use some of these algorithms. But typically what happens is the constant factors are so big, right, that actually you have to be inverting a huge matrix for it to be better to be using this rather than to be using this simple one here, right? Because also remember this guy, this is all vectorizable. We can do all kinds of things in parallel very simply. A lot of stuff can go on. We can do other tricks to make it fast, even though it's asymptotically worse. All right, so be very careful about asymptotic complexity in practice. Yeah? It's a great way, it's a great tool for thinking about things, but actually a lot of it is a game played by computer scientists. All right? And that brings me to another game played by computer scientists with P and NP. Okay, so polynomial time, you should understand, is where we're having a polynomial here, right? So we take the size of the input, let's call it n, and then we have n, a polynomial including n. So that means we can write n to the 956, right? Any algorithm which is n to the 956, you're not going to be able to solve very many examples of, right? Because 2 to the 956, well, that's more atoms than there are in the universe. So even if you have 2 of these things, right? But that is polynomial, right? And so that's anything that's polynomial is that, right? But what's NP, non-deterministic polynomial? That says, okay, you're allowed to guess a solution to your problem, and then you can check it in polynomial time. Okay, so if we think about an example, which is NP, yep. So polynomial time means the number of steps is bounded by some polynomial, right? Now, a polynomial, right, is just anything I can write. Oh, I need a way of writing on a board. Right, so a polynomial would be a naught times x to the naught plus a1 times x to the 1 plus plus an times x to the n. Right, so x is the variable here, right? I should have changed it, so let's call it n. Right, and this is a polynomial of degree n, the biggest number here, which is not 0. But I can keep going, right? There's a polynomial, I can get that n as big as I want. That's still a polynomial. So basically it says I can solve the problem in at most that many steps. All right, so all of the things here are polynomial time algorithms. All right, that's n cubed. So there is a number a to the 3, x to the 3, which bounds the amount of work I have to do to invert a matrix. Right? Each of these is polynomial time algorithms. Right, NP says, okay, I can guess a solution and I can check it in polynomial time. So let's think about traveling salesman. Right? That's an NP hard problem. Right? Why? Because if I tell you a solution, I say, here's a tour. Right? So I say, from this city you go to here, from this city you go to here. First of all, I can check it's a tour in polynomial time. That's easy, actually. To check if it's a tour, I just sort of follow, and if I hit somewhere back before I get back to where I started, before I get all the way around, it's not a tour. Right? So first I have to check it's an actual answer. And then the actual NP hard problem would be saying, can you find me a tour which takes less than this amount of time? Right? So what I do is I check it's a tour and I add up the costs all the way around and I see that sum and I see if it's less than the amount that you gave me, the limit. Right? So technically, when we talk about this thing, we have to make decision problems, right? Yes, no problems. So we can make our TSP problem into a yes, no problem by saying, find me a tour which has distance less than this. Right? And you can see, if I give you a tour, you can check it very quickly. It takes order n, right? I just run around the tour, right? I can check both at the same time that it is a full tour, and I can also sum up the costs. And if that's less than the bound, done. Yeah? So it's very, very easy to check, right? But it's not easy to get the tour, right? Right? So, and that's one of the differences between NP complete, right? So TSP, when I say the TSP problem, which is find me a tour which takes less than this amount of time, that's an NP complete problem. Okay, NP complete problem means that any NP complete problem I can map into that in a polynomial way, right? NP hard just means that in order to solve that problem, it's at least as hard as NP complete. So the TSP problem, the normal one, which says find me a minimal distance tour, is NP hard, because it's not a yes-no question anymore, right? So it's at least as hard as NP complete, because if I can find a tour, the smallest tour, then I can answer a whole lot of questions which are NP complete. Okay? Okay. So how do we characterize examples? So we talked about computational complexity. So let's look at clustering, right? So a clustering problem, I've got n points, and I assign them to k different clusters. Yeah, and what I want is that points that are assigned to the same cluster are more similar than points assigned to different clusters. Right? This is a very classical machine learning problem, actually. Yeah, been lots of ways of doing that. So here's two different clustering algorithms. So k means clustering. That first one says, okay, we just first by randomly assign our points to the k different classes. Okay? And then what we do is we find the median of each class. So if you think about points in the space, we just find the average point, right, the center point of that class, which was random to begin with. So then we'll get k different medians. Yeah? K different median points. And mean, actually, they're mean points, not median points. Then we do, so once we've got these k different mean points, we say, okay, now we look for every point, and we now assign it to the cluster to which is closest to the mean point, right? So we're going to reassign everything to clusters, right? And then we'll get new mean points, and then we'll keep going around that loop until we feel like nothing changes, okay? It may not be that nothing changes. We may have some point which alternates back and forth, but actually, typically, it'll converge quickly, right? A different way of doing it is agglomerative clustering. So here we say, okay, we'll take all of our endpoints, we'll work out all the distances between every pair of points, and then we'll say, okay, let's take the two with the smallest distance, let's put them in a little cluster by themselves, right? And then we'll take the next 2 points with the smallest distance, we'll join those up, and we'll basically do this tree of joining up until we have k left over. Right? We'll just keep on joining things which are close together until only k groups together, right? So we start off with endpoints, and then we join these two which are close together, we make them kind of 1 point, right? They're their own little cluster, and we treat them as a single point. And then we keep on doing that, keep on joining the closest points together, and then we have this, which is a pair of points, now represented by their mean. We find another one, and we keep joining them together. So we basically build this tree of joining points together until, yep.
To find the closest point, you have to just calculate the distance between all of
Yeah. So then agglomerative crossing, there's a number of choices you can do about that, right? So what you can do is you can say, let's say I have 3 points in this cluster and 4 points in that cluster. Then I'll think of the distance between the clusters, which is what I have to work out, to be the shortest one, right? If I take the shortest one between the two, that's one way of doing it. Or I could take the average, right? So there's different kinds of agglomerative clustering which work with different ways of understanding. If I have a group of points and another group of points, what do I think of the distance between them, right? But essentially they all work the same way, and they give you different kinds of answers. The simplest one is where you just take the smallest distance. Yep.
Is there any way that we could just estimate the optimal number of k or optimal number of clusters?
Very good question. In clustering, there's two kinds of clustering algorithms. So there's ones where you give the k, where you say, this is the number of clusters I'm looking for, and there's ones where you don't, right? And which they'll cluster and they'll generate it. So in agglomerative clustering, basically, you can build an entire tree and just have 1 point at the top, and then you can sort of cut at any level to get any number of clusters if you want, right? In k-means, you sort of guess k, it's given to you at the start, and because you always have k, because you have k different means and you're always moving to one. So you'll definitely get k clusters out of a k-means algorithm. But what was that k? Well, that could have been a really bad guess, right? And one of the problems in clustering is exactly that. And right, there's strengths of methods which don't need that k, and they'll generate it correctly, or generate reasonable versions, and there's other methods where you do need the k. Yep. And this is the thing about comparing algorithms, right? So strength and weakness of those two different kinds of clustering algorithms, a strength is not to be given a k, but also to give a good result, right? Okay, we can look at the complexity of these two approaches. So k-means, you can see it's fairly straightforward. I've got endpoints, right? I have to calculate the distance to k different means, and I have to do that I different times, I different iterations where I go through that iteration every time. Right? So we can work out the complexity of that fairly straightforwardly. Agglomerative is a bit trickier, and I think this is agglomerative with the shortest distance version, right? So we have to work out all the pairwise n-squared points. Then we have to sort them. Right? So we don't actually have to sort them all. We have to get the smallest one, right? Which means we have to put them in a heap. So we get the smallest one, and then we join, and then we have to get the smallest one and keep going. Right? So basically we end up with this kind of order n-squared algorithm. Yeah. So we do n joins, right, in the end, because we're taking n objects and we do n minus 1 joins until we get 1. Yeah. So that's one way of comparing algorithms, right? And as I said, be very wary of this asymptotic complexity view. It's very important. You need to be able to do it in order to talk to your reviewers. Often your reviewers will ask, okay, you've got this algorithm, tell me its asymptotic complexity. I need to know, right? In the space where I work, everything's NP hard, and so people don't tend to ask, right? You just assume that whatever your algorithm is doing is NP hard, and that's the complexity enough, right? Hard. But when you're in the polynomials, people are going to ask, how complex is your thing? But then again, it may not tell you anything about how in practice these algorithms work, right? You can have an algorithm which is order n squared, another one which is order n squared log n, and in practice the n squared log n one is way faster than the other one, right? So don't always be, I'll tell you one of the other lies, typical lies in computer science, is we have a lot of algorithms that make use of Fibonacci heaps, which have a certain best complexity for certain kinds of operations where we're merging groups together. But in practice, no one uses Fibonacci heaps because the constant factors are so high that typically for the kinds of problems that we actually care about solving, this asymptotic complexity advantage is not an advantage, right? So be very wary of asymptotic complexity. It only means what it means. And typically, because we don't solve problems going off to, right, it's true, the bigger the numbers get, the more asymptotic complexity is all you need to know. But in the end, we don't actually solve problems where the numbers get really, really big very often. Sometimes we do. Things like sorting and that kind of thing. We can solve very big things. Okay, yep.
And I know there is another complexity, like space complexity.
Yes? Yeah, so that's another thing where we can talk about characterizing performance, right? So we can talk about complexity of time steps. That's the normal way we think about it, but space complexity is equally important, right? So how much space do we need? And asymptotic space complexity is also equally misleading, right? Because actually, when we talk about space, it's very much more finite than time in some sense, right? So you can always spend more time, but if you need more space, well, you may have to go and buy a new computer, right? So we don't typically just magically add on extra memory onto a computer. But so space complexity is also important, another way of comparing your algorithm, right? And it becomes critical for very particular things like garbage collection, right? In garbage collection, do you need 2 times the amount of space that you actually use, or you just need the amount of space you actually use, right? It's a very critical difference. So the simple garbage collection algorithms basically say, okay, we take this and we copy it all over here, and then we start over here, right? And so basically you need 2 times the amount of space that you actually use because you've got to have to way to copy it somewhere else. Okay, clever garbage collection algorithms don't do that kind of thing, and they do all kinds of tricks to try to avoid that, right? But yes, space complexity is another kind of complexity. It's not the first one. When we think about complexity, we think normally about time complexity. Okay, so performance goals. So speed, is it faster than existing methods? Another one here, memory usage. How much memory does it use in practice compared to other ones? Often very critical, right? Because we know, and actually this is one of the weird things about doing computer science now, right? If you want to actually analyze how well your algorithm is doing, you basically have to understand a bit like database reasoning, right? Because your algorithm is going to perform well depending on how many first-level cache hits you get, how many second-level cache hits you get, right? It's actually going to perform, a lot of its performance in practice is going to come from memory behavior, yeah? So memory performance is also key. Okay, reliability. When and how often does it fail? So when is it guaranteed to give a solution? Okay, generality. Can it solve lots of different problems? Okay, that's the particular area of computer science that I'm interested in. So in discrete optimization, I want to build not an algorithm to solve just this problem. I build technology or algorithm approaches that solve wide ranges of problems, right? Because to me, that's a very exciting thing to do because it means it's usable by lots of people, tackles lots of things. So accuracy, particularly when you think about a machine learning problem, right? What K-means. How accurate is it? How well does it make good predictions? Okay, it doesn't make much sense. Accuracy in terms of TSP, well, you can think about it a different way. You would say, how close to optimal is the solution that it returns? Is there a bound? And so basically, each of these goals is kind of empirical performance goals. You're going to pair a metric, right, to measure the performance of the algorithm. Right, so this is where now we're getting down to the level where we can talk about what you've been talking about in the last couple of weeks, which is making a hypothesis, right? So once I've picked a performance goal and I picked a performance metric, then I can make a question, a hypothesis saying, you know, on this metric, my algorithm is better than this other algorithm, right? I've now reduced my problem down. So this is one of the differences about, like, if you're comparing algorithms, you're not going to just make a single hypothesis and test it, right? You're going to have comparisons on multiple different features, so in some sense you're going to do multiple different hypotheses and multiple different hypothesis testings. And another important thing, as I've talked about before, is if you have standard benchmarks, then you can compare, right? And that makes it easy for you, right? If you're comparing against the same benchmarks as another paper, then you can more or less just repeat their published results and your published results and see we're better, let's say, in accuracy terms, for example. Now, it's a bit harder if we want to talk about time, because in time they'll be using a different CPU and a different compiler and a different other thing. And so if you just compare raw times, then there's this whole game to play about trying to make those time comparisons fairer, right? Because lots of things will be different. So ideally, that's what I said earlier, you actually grab their code and you run it on your machine on the same data, exactly the same as your algorithm, and then you compare them side by side, right? And that's the ideal way to do it, but their code may not be available. You may have to rebuild their code, and again, then you have that problem. All right, so you perform on standard data sets against existing algorithms, because part of what you're trying to do is show that what you're doing is better. Okay. So, how do we test algorithms? So we want to test on problems which are the kinds of problems the algorithm is designed for, right? So if I've got a shortest path problem and it's designed for shortest path algorithms where the edge lengths are always non-negative, then I should use those examples. If I use examples with negative edge lengths, then actually my algorithm may give the wrong answers, right? It may not work. Or if I'm building, let's say, a machine scheduling algorithm, then ideally I want to run it on examples of machine scheduling for, let's say, my client. The examples for their examples. They're the ones they care about. They don't care about arbitrary examples. Right? So in this case, we want to use real data as much as possible. But often we don't, right, for a few reasons. Often we won't have access to real data. You'd be surprised how often even people who are talking to you and they want you to solve their problem will be unable, not even sometimes unable like for legal reasons to give you the data, or sometimes unable for technological reasons. They just can't extract the data from their systems, right? So you'll work on fake data. The other advantage of synthetic or fake data is that you can then adjust it, right? So if we're doing some algorithm which works on, let's say, classes of linear constraints, I want to check, okay, how does this work if I make the coefficients in the linear constraints very, very big, right? How does it work if I make the number of variables in the linear constraint very, very large? Right, so I want to adjust different factors of the input to see how that affects my algorithm. Yeah? And that's what I can do with synthetic data. So it's quite valuable to have the synthetic data, even though it may not be showing you, something about the real usage of the thing. But it shows you like scaling with respect to some part of the problem. Right? It begins to show you how your algorithm compares against our other algorithm as one parameter in the problem changes. So that's the value of synthetic data. And, right, you should measure the variation across lots of instances, yeah? So you've got to be very careful, and this is often the case if you have one real-world sample, right? So maybe you've got one scenario out of your client, which is this is the problem I need to solve. Here's an example. This is Monday on September the 10th, right? This is what it took. And you solve that problem, and then you work on it. You can solve the problem better and better and better. But actually what you can be doing is just tuning your algorithm to that one piece of data, right? And then we get September the 11th, and it does terribly, right? So one instance is very, very misleading. So you need to be looking at lots of different instances, and ideally unbiased sample, right? So another problem is that you only really get one set, you only get September the 10th, and then you do some randomized sort of variations which seem reasonable to keep it like the same, but it ends up that you're not really varying it enough. And actually, if we look at the real data that they see on September the 11th and 12th, it looks very different and your algorithm doesn't work very well. Okay, but the key thing is this: you need to make fair comparisons with leading alternatives. That is, if you can't use their code, right, or get it to run, then you re-implement it as well as you can, not as badly as you can, right? And actually a lot of papers in the world ignore the problem, right? Ignore all the previous work, and they build a very straw man solution, like the simplest way you might tackle this problem, and compare against that, and show, look how much better we are, and in reality that's not very convincing, right? And what the referee should be doing in that case is saying, hang on, you didn't compare against these methods, because you need to compare against the state of the art, ideally, right? That's what you're trying to do. And another thing critical, and I guess this is particularly in the learning space, is that you can't sort of build your solution based on the data that you're going to actually test it on, right? As I said, if I'm only given one data set from my client and I build a solution which works really well for that data set, then that's not very convincing, right? So particularly in machine learning, you want to separate your data sets into two parts at least, maybe three. So you have the training set, which when you're testing your algorithm, you'll only use the training set, and then the testing set, when you actually evaluate your algorithm, you evaluate on data that it's never seen. Yeah? Okay, and what's the right metric to use for a problem? Well, typically you want to look at different ones, right? Speed, that's the obvious one. That's the first one we go to, but as we said, space is important too, right? And even when we say speed, what do we mean? All right? Is it lower computational complexity? So you can actually prove that your algorithm is algorithmically lower computational complexity. Almost certainly you'll get a publication out of that, because that's a sort of theoretical computer science result. So these guys who proved that they can do inversion in n to the 3.73, right, 2.373, certainly that's an interesting publication, even though the algorithm's never used. That's a different way of judging things. I'm just going to get to the end of this section and then we'll have a break, by the way. Reliability, right? If the algorithm doesn't always work, how well does it fail? Accuracy, as I said, in predictions. How good are its accuracy measures? And there are lots of different ways of measuring accuracy, right? You can do mean squared error, you can do precision, refall, area under the curve, all kinds of things. And there's often specific tasks that have their own evaluation. So tasks that we've been doing for a while, we've actually built up not only data sets to test on, but also evaluation metrics, like the right way that the way you judge your answer to be best. All right? How much are we going? I'm just going to see. Oh, we're almost there. We'll have a break at that brat. Okay, where was I up to? Okay. And so that's what I was talking about. There are standard data sets out there, right, in lots of different areas. So, for example, the Boston housing data set has all these different data, and we can learn on it. We can try our different regression methods, looking at these different attributes and working out whether our way of predicting, let's say, housing prices is better. And the other thing is that there are competitions, right? So we now often have competitions for particular kinds of problem sets, right, where everyone puts in their own algorithm and then they're run by a competition organizer on the same data sets and then they're compared, right? And so this is really nice because it basically generates standards, right, because all of your programs have to read the same data, right, the same format, data. So that's good. It gives you a common environment for evaluating the code, right? So, and then you can look at all the results in detail. And often one of the great things about competitions is not actually like who won, but it's when you look in detail at results and you can see, look, this algorithm is very, very strong for this class of instances, right? Or this algorithm is very, very strong for this other class of instances. But you've got to be careful. Competitions actually drive innovation in one particular direction, right? And so if you have a competition like, let's say, like the SAT competitions, which is running for a while, all of the benchmarks they use a lot of industrial benchmarks, but they all come from the same space. They're all either cryptography or circuit verification, right? And SAT is used for a lot of other things than that, but this is the sort of two big areas where it's used. And so what it does is drives the SAT solvers to be good at circuit verification style problems and cryptography style problems. But there are other SAT style problems out there. So, for example, the French Soccer League, right, is scheduled by a guy in Barcelona who uses SAT solver. But if you use any of the SAT winning competition solvers on those problems, they'd have terrible performance, right? Because they're all tuned to a different class of problem, right? And the Soccer League scheduling problem is a SAT problem, but a different kind of SAT problem, right? So you've got to be careful about competitions that they can drive everyone to do better and better at this class of things that just tested in the competition, but that may not be everything that we're talking about that could be done. All right, so there's examples of different competitions out there, and in fact, I run this competition, so there you go. I believe in competitions, even though I understand the dangers of them. All right, let's finish it off. So in machine learning, there's a very specific methodology, right, that we basically have to get used to, and many of you have been involved in this. So if we're developing a new prediction technique, a new regression or classification technique, then we have to basically always do these steps, right? We have to split our data sets into three parts. A training set, right, that's how you learn the model. The validation set, and this is because whichever way you're learning a model, there'll be some parameters that you can adjust in the learning algorithm, and you use the validation set to tune those parameters to get the best set. So if you're using agglomerative clustering, for example, like which style of agglomerative clustering should you use? All pairs distance, minimum distance, right? So there's parameters you can choose in your learning algorithm. You use the training set to get those right. And then finally, a completely different set, right, the test set, and that's how you evaluate how good your algorithm is, right? And this is a very critical thing in machine learning particularly. You cannot test your algorithm on the same data it was trained on, right? You'll just get completely misleading results. And so there's lots of repositories to help you evaluate performance, right? There's software tools that help you build or evaluate algorithms. And so, for example, in the machine learning space, there's large numbers of like toolkits for machine learning, right? Like TensorFlow, and I'm trying to think what it's called, LabKit or something. Famous ones. There's reference implementations of various algorithms. So that's nice. If there's some standard algorithms built with the reference implementation, you can run against the reference implementation, right? And see how good you are. There's benchmark data sets out there. And there's metrics for performance evaluation, or even competitions to do performance evaluation, right? And you can develop tools that help this, right? It's useful for the research community, and it actually is another form of publishing. And indeed, you'd be surprised, building a good tool set which is widely used is a very good way of generating large numbers of citations, right? Okay, so we'll finish off this section by just putting up some data repositories that are out there, right? Interestingly, like the government has lots and lots of interesting data, yeah? And they make it available so people can play with it, because it's useful for them if some people come up with good ways of doing things. And there's repositories for algorithm research. There's a few there. Well, things like SourceForge or GitHub are the new ways of doing it. Okay. So that went for too long. Let's have a 10-minute break. So, well, let's start at 10:20 again. So it's not quite a 10-minute break. And we'll look at case studies in evaluating algorithms. I have to bring myself some water. I'm out of practice. But take advantage. If you've got questions, you can ask me questions. But yeah, if you need to run away, escape my continuous onslaught of information, feel free. Oh. All right, let's keep going. All right, so the second part, let's just look at two case studies of evaluating algorithms, right? So this is the whole purpose that we're talking about today is, okay, how do we evaluate our algorithm to see whether it's better or worse than something else? And we'll look at a regression style algorithm and the TSP, which is an algorithm for a hard or search problem. Okay, so the group method of data handling is this ancient, 1966 is ancient in computer science terms, right? Approach to fitting, basically it's building a regressor. So if I give you some data input, so a single value regressor, it'll produce an estimation about where that is. And it actually works by building these pyramids of polynomials. So if you have, let's say, 8 inputs and a single output, right, it's only for a single output, it'll build up a polynomial that joins these things together to eventually produce this regressor. So this is a prediction of the y value you should get if these x1 to x8 values are input. So it was used in lots of studies, okay, before it was actually tested for the first time probably in 1988. Right? So what should we be doing if we're looking at a regression algorithm to seeing whether it's effective? Okay? So if we ask the question, how well does this GMDH regression algorithm work? So we need to answer some questions. What does it mean to work well, right? So we can answer more than one question. So fidelity, right? If we give it some known patterns, right, synthetic data, how accurate does it work, right? So we use some artificial data with a range of properties just to see how accurate it can be on those particular artificial examples, right? Just to see how accurate it is. So robustness, so we can take the same algorithm and the same data input and we can add noise, right? Add more and more noise and see how does it change as we add more and more noise, right? And then finally, utility. If we look at real-world problems, how good is it on real-world problems, right? So maybe that's what it's meant to be used for, right? Case studies, real systems of different kinds that have already been studied, right? How well does it work, right? We could also compare it against other algorithms. We don't need to do that here. Okay, so GMDH is it's a regressor. So it's given, you're basically given some points. So here's the actual data, this y equals log x, right? And it's given some test points in this testing range from here to here, and it comes up with a solution. And so when given some points in here, it basically came up with this quadratic function, right? Which you can see is not very close to the log x function, okay? In the testing zone, it's not too bad, right? Pretty bad when we get down here. But outside the testing zone, like it's really terrible over here. Okay, over here, I mean, there's no actual test points. So it's even a meaningless question. Or maybe it doesn't matter, right? The error over here, if the answer here is no answer, maybe it doesn't matter. Right, if we look at 1 on x, you can see, so these are the actual values, the dotted values, and here's its prediction, right? So some kind of quartic there. And you can see that, okay, it's kind of, you can see it's sort of okay in this testing zone. As soon as we go outside the testing zone, it just gets ludicrously bad. Yep. And really bad kinds of examples for this are very simple functions, but which don't have good polynomials, right? So here's a step function. It just says to take this value up to here and then take this value here. And you can see it's produced a very big polynomial, probably like that's order 8 or something, right? Polynomial, and it's pretty terrible, right? It's not at all reflecting the reality of it. Right, because it's got a limit in its expressiveness. It's only going to use polynomials in the end. Okay, how about logistic regression? So here, again, within the testing zone, looks pretty good. Outside, terrible. Sin x. So again, within the testing zone, well, it's not that good, but you can see what it's trying to do. Right, here, interestingly, you give it a different testing zone and it's spot on. Okay? So, as you can see, the GMDH sharply deviates outside its testing range, outside its training range. Yeah. All right. So, first question: is it accurate on synthetic data? Well, not really. Somewhat accurate within the area where it's tested, but remember we went to test in one area, train in one area and test another, and when you're outside that testing interval, it's pretty terrible. Okay, if we look at a model and we just increase the amount of noise that we gave in the training set, so what happens? So if we have no noise, then the actual model is perfect, right? But only like 50% of the variance in the data is actually explained by GMDH. In the best case, no noise, right? When we add 50% noise, then obviously the simple regression is not going to be able to explain everything, but you can see it's way worse than that. And interestingly, once we get 100% noise, then somehow we're good, because basically there's nothing left to predict at this point. So when there's nothing left to predict, then GMDH is as good as anything, right? So as good as random, which isn't saying very much. So basically it shows you that it doesn't do very well in the prediction under noise either. And then finally we look at some real data. Okay, so here is some Sydney rainfall data. Okay, this is the testing period. We have a training period for the 6 years before, and here's the 6 years after, or the 5 years afterwards. Right, this is every month. There's the actual data. So if we do a training using maximum temperature in hours and sunshine for the current month, so we've got to pick what are the inputs, right? So they're the input data that we're using. You can see, does this graph look like this graph? Well, something like there's a peak there, there's a peak there. That peak doesn't seem to be on, right? So it doesn't look like that much at all, really. I mean, it's hard to align that data with that data, right? So not very impressive. Okay, if we added in the rainfall for the current month, right? So you're allowed to you're just predicting 1 month ahead. So you think it'd be a much more easy thing to predict, right? You can see, you know, the model changes completely and it looks even further from this thing here, right? And if we built 10 different models, like Model B, where we're using different sets of orderings, and we took the average, so we hope if there was some learning that GMDH was actually happening, that if we took 10 different models and take the average, then we should be able to capture something. And if you look, I mean, it's sort of said, okay, there is a big peak here, and there's kind of some peaks here, and there's kind of a peak here. So it's sort of giving some macro level detail of this data, but otherwise it's terrible, right? So in the end, GMDH, which has been used for hundreds of different things, was just actually a very, very bad regression algorithm, right? And this should have been done when GMDH was originally published, right? Of course, this is the problem with science, that if it's not tested well, you can make really terrible algorithms look good, right? So, right, if we look at this question, how well does GMDH work? We tested the fidelity. Can it reproduce known functions? No. Actually, it can produce some linear or polynomial ones it can perfectly, but typically not if we go outside its testing range. Is it robust to noise? No, it wasn't robust to noise either. Was it good on real data? No, not really. Okay? So it's actually performed worse on the systems where it's meant to perform best, right? On these known functions. Yep. So it can't even match simple regression. So it's a really, really terrible method and should never be used. Yeah. But the good thing about this is, well, the bad thing about this is that this was used by many, many people without really asking these questions, right? But it is, tackling these questions also suggested ways to do better things, right? If you say there's something wrong with this algorithm, it also gives you ideas about how could we change, how could we make it better. All right. How about case study number 2? So as I said at the beginning, search is central to many hard computational problems. In fact, this is the area that I live in. My research interest is principally here. Okay, so for example, if you're doing doing a machine learning problem, then one thing you have to do is parameter tune, right? Searching for the best parameters for your algorithm is a search problem, right? So there's lots of approaches to search. So depth-first search is trying to go as far as possible, right? As deep as possible. Breadth-first search is trying to look as close as possible, sort of trying to find the shortest ways to doing something in terms of number of steps. Incomplete versus complete search. So if we think about many of these problems, there's actually only a finite number of possibilities, but I'll show you it's a very large number, right? So an incomplete method will only look at some of them. Is not guaranteed to find the best. A complete method will, given enough time, right, look at every possibility, or not, ideally won't look at every possibility, but it'll consider every possibility and definitely find the best answer, right? And so there's other ways of also doing search which use problem reduction. So you might say, I will break this into points. If I'm doing my routing problem for bread, I might say, well, I'm going to do every state separately. Right, so the trucks in Brisbane, or the trucks in Queensland are only going to deliver to Queensland, and the trucks in New South Wales are only going to deliver to New South Wales, and so that makes my problem smaller because I've basically got independent problems, but of course that might be really bad. Right? Brisbane is really close to New South Wales. Right, so why shouldn't some of my trucks in Brisbane go and deliver to some of the parts in the Gold Coast, which is closer than Sydney is to the Gold Coast? It might be much more efficient. So divide and conquer. Sometimes we can do divide and conquer and get perfect answers. Sometimes we give up by making the problem smaller. And we're going to look at this classic hard problem, travelling salesman problem. And one thing we should know is there's a no free lunch theorem, which basically says any algorithm for these NP hard problems, these search problems, there'll be bad cases for it, right? So there's no algorithm which will be best for all problems. Yeah? But that doesn't mean that we can't find an algorithm which is really strong for all the problems we're interested in. Because there's lots of problems which we'll never ask. Okay, so travelling salesman, right? I'm just going to give you a set of cities to visit, and you need to find the shortest path that connects them all together in a big circle. Right, so example, if you look at this example, this to me looks shorter than this, right? We're all going around the same. We're visiting all the cities, and I think the total edge length here looks shorter than here. It's not so obvious, right? So it shows you why. Now, if you think about it naively, right? There are a large number of ways to visit all those cities in order. How many? If I give you n cities. How many ways to visit them all in order? Well, n factorial, basically. Slightly less because I can just pick one as the starting point. It doesn't really matter. Let's think about just if we try to do this by brute force search. Right? Brute force search, we'll sort of do our NP problem by saying, okay, we'll just try every possibility and check them. And then we'll check them, and the one which is the smallest, we'll keep that one. Right? And brute force search is fine for lots of things. So if I want to find the largest town in population, let's say, and I've got n towns, and brute force is easy, right? I just have to look at every town, compare, and keep the biggest one I found. It's order n operation, so basically only takes me a few. In fact, that should be 40 and that should be 50, I believe. And that should be 1600. So I never noticed that these tables are wrong. Okay, what if I need to find the greatest distance between two towns, right? Basically, then all I can do is work out all the n squared distances, right? Or it's in fact n times n minus 1 over 2, right? That's the number of pairs of towns. And calculate all those, and then look at the smallest one, right? So basically, that's the cost. N times n minus 1 over 2. But actually, this is n squared that's being written here. But basically, it's order n squared. Yeah? Okay, what about finding the shortest route connecting all towns? Well, if you think about it, there's kind of n factorial routes, right? Because let's pick an arbitrary starting point. So then I've got to order all the rest of the n minus 1 towns. So I've got n minus 1 choices for the first one, and then n minus 2 choices for the next one, n minus 3 choices for the next one, n minus 4, blah, 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 n minus 1 factorial. Right. I think there's a division by 2 because there's 2 directions. I could go this way or I could go around the other way, and so I can halve the choices in the first one, right? So I avoid all these 2 symmetric tours. And what you want to see really is how these numbers grow, right? So at 10, we're looking at 181,000 possibilities. At 50, we're looking at 3 by 10 to the 62, right? So that's just not a number that you're going to, that's a number which you can't even count from 1 to that number in your lifetime on a modern computer, right? So the cheapest thing you can do on a computer is sort of add 1, right? So you can't even do that in a time which is reasonable. Yeah? And that's size 50. So brute force is not going to work. Right? The number of, this growth in the number of possible tours is huge. Right? So saying, I've shown you that table. How big a TSP problem do you think we can actually solve to optimality? Right? So if I go back to the table before, right, let's take the brute force solution, right? So you can see like 10 to the 16, that's a kind of small amount of numbers. 10 to the 30, now we're getting big, right? So even that, iterating from 1 to the 10 to the 30, you can do in a time. 10 to the 46, pretty big. Okay, that's 40. I want you to give me a guess. Everyone has to give me a guess, since we've got a small number. How many do you think we can solve to optimality? As in prove this is the very best possible tool. What's your guess? Come on, just a number between 1 and infinity. No, come on, make a guess. There's no penalty. You can just win. 100, okay? 100. Next. 50. 10 to the 20. 10 to the 20, that's a huge amount, okay? It's good. 500. 10 to the 900. Wow, these are big numbers. That's the number of cities we're talking about. Yep, go.
Well, number of cities.
Yeah. Okay, what do you mean?
Okay, I don't know, like 20.
20? Okay, that's a bit different. So, 50. Okay, next. Yeah, how many cities do you think we can solve to optimality with travelling salesman? 50? 50 is very popular. I should have made you all pick a different number. Let's go. 1 million cities, okay? 500 cities. Okay, so we got some big numbers, some small numbers. Okay, the best known approach can solve about 90,000 cities, okay? So that, if you think about that chart on the previous chart, it's not a million, okay? Can't solve a million, but 90,000 cities, you think about 90,000 exponential, it's just way too big, right? So the whole point of complete methods of solving these problems is we're not going to do anything that is brute force, right? We have to be clever, right? So it's based on a very special integer programming solving approach, right? And it takes advantage of the structure of the problem, right? So that's key. The more we understand the problem, the better we can do. So we proved that even though we sort of have to look at 90,000 factorial possibilities, most of them we never look at, obviously. We don't even look at any small proportional, right? So this is the thing, that thinking about a problem hard, you can go a lot further than you think. We're doing way better than brute force, right? That's what algorithms are trying to do. Not try to do the simplest thing, try to do the best thing. So, but when we need to solve bigger TSPs than that, and indeed, so we have to as well, and so we often, in the end, do approximate solutions, right? And so the approximate solution is very simple. Generate random tours. Okay, this is a simple way. This is not the good way. I'll show you a better way in a simple. Generate some random tours, work out how much they cost, and just keep the best one you found so far. That's a very simple random algorithm, right? We can do divide and conquer. Divide and conquer actually is terrible for TSP, right? Because if you think about it, it's one big circle. If you try to divide it into bits, you're not really making any sense, right? Do a circle here and a circle here, joining them together doesn't really tell you very much about the whole circle, right? So divide and conquer is rather terrible for TSP. It's not used for TSP in general, but often it is a useful thing, right? When I talked about the vehicle routing for the trucks, right? Dividing it into separate places makes sense, makes the problem easier. Okay, so in solving these hard problems, we often need to search, and we're not going to be able to find the best solution. So you can think about it as kind of this notion of a fitness landscape. Right, so you've basically got the cost of each of the tours, and these are all, this is a two-dimensional view, and obviously this is, in an n-dimensional case, there's lots of dimensions. Basically, there's the value of that tour, and you're trying to find, let's say, the global maximum or the global minimum, right, across this big landscape. So these search problems all turn out to be like this. Right, so you can be systematic about this, right? You can just try every point that fits in the grid, right? In two-dimensional case, that makes sense. That might find you a good solution. You might miss the best solution, right, by far. Or you can do local search where you sort of start in one point and ideally feel like what the slope is at that point and then try to head towards a better solution. Right, and that's a very, very common approach to tackling these kind of search problems. Although it's not going to get you the optimal solution, because what typically happens in a local solution is that you sort of start here, let's say, and you go up and you get to here and you go, oh, there's nothing better. And so I stop, right? Whereas actually there's a way better solution over here, right? So typically in local search solutions you need two ways. You need to be able to go up to find better solutions, but you also need to be able to jump around a lot, okay? To be able to get stuck, get out of being stuck. But there's really this two class of methods, right? Incomplete methods, so they don't guarantee to find the best solution, and they typically are local search methods, so they here at some position, they change something and they see if it's better, and they sort of keep moving trying to find a better solution. And they got other methods to jump around a bit randomly to get to a new place to maybe find a better solution where they are. And then complete methods, okay? Like I said, for the TSP, we can do the Concord method, which is complete. It'll find the optimal solution given enough time, right? So if you give Concord a million city problem, it will find the best solution given enough time. But the universe will probably end before that enough time, right, comes to an end. And they typically search in a very different way, right? I'll try to show you in a moment how it works for TSP. And incomplete methods, so their advantages is they scale to very large instances, and they're typically much easier to implement, right? The disadvantage of them is that it can be very, very bad if you have lots of constraints. Okay, so if you think about the the vehicle routing problem, right? The travelling salesman basically has no constraints. We can just pick an order and we can check, right? But in the vehicle routing problem, the bread has to be delivered to this customer between these hours. And it has to be the same driver on Monday to Friday, but not on Saturday and Sunday. And lots of other constraints go into the problem, right? So there's a lot, it's not just the routing problem, the travelling salesman problem, but all these other constraints about when the truck arrives, can it carry enough bread to visit all the people, lots and lots of other constraints. And typically, incomplete methods aren't so good because you can't just guess a solution because it typically isn't a solution. We have to make sure it satisfies a whole lot of constraints, so it gets hard to guess. Yeah. So complete methods have this big advantage that they can find optimal solutions, or even if they can't find optimal solutions, right, because you run out of time, they can often say, well, we know you're within 3% of optimality. Right? We don't know what the optimal solution is, but we know you're no further than this distance from it. So that's really nice. Gives you bounds on the quality. And of course, the cons are they require more expertise to use, right? And often you build a new approach for each problem. And I guess what I'm most interested in doing is building complete methods which are generic, which work for lots of problems. That's what I do. That's my part of the box. But in the end, obviously, we use them as local search methods too. So let's have a look at TSP. So here's a very classic way, right, of local search for TSP, which is really, really good. Okay? So you start with an initial tour. So you can start with a random one, or you can just sort of go pick the nearest neighbour and just point them to the nearest neighbour, and then you perturb the tour. So this is what the local swap is. You say, okay, let's do a two swap. So basically we'll pick some part of the tour and we'll change it, we'll flip it in one direction. And you keep the new tour if it's better. And then you can do four swaps as well. I'll show you a two swap. Right, so this tour, right, is A, D, C, F, E, B, A, right? We just pick this little area, F to E, and we'll swap it. Right, so we get A, D, C, E, F, B, A, right? So we swap that whole thing, and if you think about what that looks like, that's what happened, right? So C used to go to F, it now goes to E. E used to go to B, it now goes to F, right? So this area is swapped, and B used to come from E, and now comes from F, right? But in the middle, okay, here it was only one, but there could have been a whole tour between E and F, and basically we reversed the direction of all those arcs. Yeah, but nothing changed. So basically you can see that we've taken this tour and we've made a shorter tour, and so we'll keep going from there. Right? If it was longer, we would go back and try a different thing. Right, so even if you just take, if you take problems of size 100 or so, and you only do two swaps, you almost always get very close to optimal answers very, very quickly. Okay? In Euclidean graphs, which is the normal one. You can also, in order to do better, you do four swaps. So four swaps allows you to escape from local minima, which you can't escape from with two swaps. And I'll just show you what it looks like diagrammatically. So if this is your existing tour, a four swap basically says we take four places and we swap where they go. And it's why it's called a double bridge, as you can see. We sort of form this double bridge, right? The two bridges cross each other. And basically, you can't get this by any number of two swaps. All right? So it allows you to look further away. Yeah? And so this algorithm by Kernighan and someone else, I can't remember, is very, very good at finding very, very good tours of the TSP very quickly. Yep, so that's a local search algorithm. Doesn't find the optimal. So how do we do a complete approach to the TSP? Well, actually we're going to start by running the incomplete approach, right? So if we get a very good solution first off, then it gives us a bound, right? So, because if we have a bound, we're saying we already know a tour which takes us, let's say, 100 time steps, then if we ever find that any tour that we're going to build from here takes 110 time steps, we know it's no good and we can not look here. Yeah? So, we'll start with an initial very good tour, right? So we'll have an incomplete approach that will give us an upper bound on the solution that we want. And then we're actually going to have to make decisions, right? Because we're going to have to essentially make sure we check every possible tour, right? So let's say we're going to guess that from C, the next place we go to is F, right? Imagine that that is the case. We're going to say that. Because from C, we have to go somewhere next. We have to go to somewhere else next. So there's only, in this case, 5 possible other places we can go. So this is one of 5 things. This separates our tours into 5 different classes. So if we do that, well, we can reason about this. Any tour which includes this edge, must have at least all the other nodes joined together, right? So we have to visit everyone else. And the shortest way we can join those together is the minimal spanning tree, right? So any tour which includes C to F must have at least an extra distance which is the minimal spanning tree of the rest of the nodes. Yep. Now, if we add up all of this minimal spanning tree distance plus this edge distance, and it's longer than the path we've already seen, then we know there's no better tour which has an edge from C to F. And we've wiped out 1/6 of all possible tours in one go. Right? Straight away. Okay, it's because a minimal spanning tree, remember, is the shortest way of joining together n things. Right? It's not a tour, so the tour will be longer. Yeah? So we can basically immediately add, in this case, that you can't go from C to F next, ever, in whatever tour you're talking about. And so basically we do this, what's called branch and bound search. Make a guess and reason about if we've made these, or we have to make multiple guesses in general, if we've made these guesses, can we get a better tour than the one we've already seen? If we can't, we can just stop. And basically we continue until we've discovered all possible things. Yeah? And that and a whole lot of other sneaky tricks are used in Concord to get it down to be able to work out things of size 90,000. Right? Because we're reasoning this reasoning. A tour is longer than a spanning tree plus one edge. Because a spanning tree only has n minus 1 edges in, and a tour has n edges, right? Okay. As I said, TSP is a very well-studied problem. It's got lots of applications in planning. I've told you one is logistics, DNA sequencing. We can get complete methods up to 90,000. Incomplete specialised methods, many millions. Right, we can do tours up to many millions, and they're very close to optimal. Of course, typically for these big problems, we don't know the optimal answer. Right? If we try generic specialised methods on TSP, they're nowhere near as good as these specialised methods. Right? So basically, search problems are very widespread, and these generic approaches are good. Complete search is methods like integer programming or constraint programming or SAT, where you need to formalise the goal of the search. Incomplete methods like hill climbing, simulated annealing, and genetic algorithms, they basically just need an evaluator. If you give me a potential solution, it has to tell you what's the value of that, so that you can use them in an easier way. Just to finish off, so if we look at simple hill climbing methods,